Okay, now come back to this second half of this lecture, and so far we have been seeing that if the ring is Noetherian, then the finitely generated modules are also Noetherian, and from this we deduce many facts. Now I want to conclude something about the ring from the modules. So for example, I wanted to conclude about the ring when it is Noetherian from the modules. See, in general philosophy of the commutative algebra is if you want to study commutative rings. So, if you want to study A, you not only study ideals in that, but study the whole modules. So, study the whole category of modules A mod and try to get information about A from this category of modules. So, this is very big data. It contains, these are collection of all modules and module homomorphisms, and in particular it contains also the ideals and so on. So, therefore, in general we want to deduce properties of the ring from this module. So, that is the general philosophy of the module theory. And before I state the result, I want to also recall whatever we proved in a last lecture for Noetherian modules. Similar statements you can conclude for the Artinian modules. For example, so the lemma, this is the lemma which is an analogous lemma which we have proved earlier for Noetherian rings, modules or Noetherian rings. We have proved that finite modules or Noetherian rings are Noetherian. Now, this is analogous lemma for Artinian. So, that is finite modules over Artinian rings are Artinian. This is the same way you prove it. If you remember how we proved that, we proved it is enough to prove that cyclic modules are Artinian or Artinian rings, and the similar arguments will work for this also, because every time you have to prove that submodule and the quotient module are Artinian, then the middle one is Artinian. So, this I will not leave, there is a proof is analogous to that of finite modules over Noetherian rings. So, write the proof, write the details. All right. Then whatever the corollaries we deduce, the same corollaries I will write here. So, corollary 1. So, A is a subring of B, these are rings, and with A Artinian. That means that the module over A is Artinian module and B is a finite A module. That means B as a module over A is generated by finitely many elements, then B is also an Artinian ring. Okay, this is corollary 2. The same way, because if you want to prove somebody is an Artinian ring, then you have to prove that it has a DCC on ideals. But DCC on ideals, so it is a finite module over A. So, therefore, it is sum of cyclic modules. So, it is enough to do it for one and so on. Okay, so, the next one, let A be a Artinian ring, and B is a finite, be a finite A algebra. Finite A algebra means, remember, finite A algebra means as a module it is finitely generated. Then B is also an Artinian ring. For Noetherian rings we have proved stronger result, which was a corollary to Hilbert basis theorem. Not only finite A algebra, but finite type A algebra is also Noetherian, and unfortunately that is not true for the Artinian ring. So, that one can write down an example. So, finite algebra or finitely generated algebra, finite type algebra or a Artinian ring may not be an Artinian ring. Okay. For example, field is an Artinian ring, but polynomial algebra or a field, this cannot be Artinian, because we can always write down a descending chain. So, let me write down as an example. This is also may be important sometime. Example, let A equal to K be a field and hence Artinian. Ring, because there are only two ideals 0 and that, and B equal to the polynomial ring over K is K algebra of finite type but B is not an Artinian ring because the descending chain ideal generated by x, ideal generated by x square, this is properly contained, and keep doing it, ideal generated by x power n, properly contained in ideal generated by x power n plus 1, this is not stationary. So, you cannot, this is the first difficulty for Artinian ring, that a finite type algebra or Artinian is not Artinian. All right. So, let us come back to our theme, that I want to conclude something from the modules to the rings. So, this is the theorem we will prove. So, let A be a commutative ring as usual. Commutative I will not say, mostly we only when I will say when it is not commutative, and V be an A module. Then the following are equivalent. One, V is a Noetherian A module. But you cannot conclude A is Noetherian, but we can conclude something closer to A, the ring. So, what is that? So, 2 Of course, if it is Noetherian module, V is finitely generated, V is a finite A module, and the quotient ring, the residue class ring. A modulo annihilator of, I will recall some basic facts about this. This is a Noetherian ring. So, let us recall what is the annihilator, and then we will prove this result. This is very simple. So, we are recalling the definition. So, definition, let V be an A module, then the annihilator and later of V denoted by ANN AV. This is by definition, it annihilates V, that means it kills V, all V. So, this means all those elements A in A such that A times V is 0 for all V in V. So, this is obviously contained in A, and this is clearly an ideal in A. That is because it is closed under addition, closed under subtraction, and also it is closed under arbitrary multiplication in the ring. So, this is clearly an ideal, and this actually gives information about the module also, because so we have because it is an ideal in A, we have this natural surjective residue class homomorphism A going to annihilator of V. The A module structure on V and A modulo annihilator AV. So, first of all, there is a structure of this A modulo annihilator of A module structure on V. So, what is the scalar multiplication? Scalar multiplication is A mod annihilator of V cross V to V, this map which satisfy the compatibility conditions. So, this is A bar comma V going to AV. So, this does not depend on the representative of V. So, therefore, the A module structure on V and A mod annihilator A module structure on V, they are identical. So, therefore, whenever there is a submodule of V, there will be an A mod annihilator submodule of V, and so on. So, whenever you want to talk about ascending chains or descending chains of submodules, we can always assume they are the base ring by passing on from A to this, nothing will change about the module. That is the most important fact. So, now let us come back to the proof. So, before I close, this is also, you can also think this is, so this is also same as intersection of annihilators of elements x in V. If it annihilates every x, then it is annihilate V, and conversely, and these are also ideals. All right. So, now let us prove the earlier theorem. So, proof of theorem. So, I have to prove 1 implies 2 and 2 implies 1, all right. So, by we may assume that annihilator of B is the annihilator of A is 0. Replace A by this quotient ring. So, what is the first statement? First statement is the first statement is the Noetherian module. So, if I would have replaced A by the annihilator of V, the module structure, the A module structure on V does not change, and the second one V is the finite A module and the residue class ring is Noetherian. So, now therefore, we can assume, because the chain conditions are, they do not depend on A, but they only depend on A mod annihilator. So, note that chain conditions on V do not depend on A, but only on A mod and I mean whether you take either the A module or take it as a A by annihilator module, it is the same. Okay, so suppose you want to prove 2 implies 1. So, what is given in 2? In 2 we have given V the finite A module. And the ring, now our ring is the V by A by annihilator of V. So, A is Noetherian now. Because you have replaced A by this. So, therefore, the second assumption in 2 was V the finite A module and A mod annihilator is Noetherian, but A mod this we have A replaced by this. So, these are the assumptions, and from here what do you want to conclude? One says V is Noetherian. A module. So, obviously, this implies this we have proved earlier that if you have a finite module over a Noetherian ring, the module is Noetherian. Conversely, 1 implies 2. Now, V is a Noetherian given V is Noetherian A module. Then we want to prove that V is Noetherian, V is finite A module and A mod annihilator of V is a Noetherian ring, but Noetherian implies finitely generated, we have proved earlier. So, V is finite A module, this is proved earlier. Now, we want to conclude A mod annihilator of V is a Noetherian ring, all right. So, V is the finite module. So, let us choose a generating system. V is Ax1 plus 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 Axn, because it is a finite module. This is a generating system, and the cyclic modules, note that the cyclic modules are Noetherian. And what are these isomorphic to? That any cyclic module that is generated by one element, this is isomorphic to A modulo annihilator of this element x. The map is, you map any A to A times x, and obviously the kernel of this module homomorphism is precisely the annihilator of x. All right. And what is the, so therefore, if I denote AI, these ideals AI by definition annihilator of the generating element xi, then what do we know the annihilator of A? So, annihilator of V, this is the intersection of a generating set, annihilators of the generating sets, which is A1 intersection A n, and let us call this as A. So, A is the intersection of these ideals, and what is then A modulo the annihilator of this V? This is A modulo A, which is A modulo A1 intersection A n, and each one of these is Noetherian module. So, therefore, it is enough to prove. So, enough to prove that the following lemma. So, what is the lemma? All right. So, if W1 to Wn are A submodules of the A module W, over arbitrary, A is arbitrary, A over arbitrary ring A, if W mod W1, W mod Wn are Noetherian, respectively Artinian, A modules, then W mod W1 intersection Wn is also Noetherian, respectively Artinian. This is very simple proof. I will just say that by induction on n, enough to prove for n equal to 2. For this, use isomorphism theorems. So, that will conclude this ring is Noetherian. So, we would have finished the proof. All right. The similar statement for an Artinian modules will not be true. So, let me write one example. What similar statement to what? The theorem. So, example, this is to show that if V is an Artinian A module, this was Noetherian A module was the first condition in the theorem, then V mod annihilator of V is an Artinian ring. So need not be, not V, sorry, this is A. Then this need not be an Artinian ring. So, the above theorem is not true for Artinian ring as it is, we will have to modify it. So, what is the example? Remember we have seen in earlier that the module Q mod Z, remember what did I call it? Z bracket 2 here. What was Z bracket 2? Z bracket 2, these are all fractions A by B such that A, B are integers, B non-zero and B is not divisible by 2. So, B 2 does not divide B, only odd denominators come in B. So, and we have proved that Q modulo this is a submodulo of Q, this is a Z submodulo of Q, our base ring is A equal to Z. So, we have proved earlier that this is an Artinian Z module. So, that is because there is if you try to find the chain, that becomes a finite chain usually. So, therefore, it is Artinian. There are no proper this is proved by using that every submodulo of this Z submodulo of Z2 is generated by a power of 2 and therefore, the descending chain will become stationary. So, this proved earlier. Alright, now let us see what is the annihilator of this. So, the annihilator of this, annihilator as a Z module of Q by Z, this bracket 2 is 0. That is very clear because what do you want to check? The only element which annihilates here, every element is the element 0, because you see the Q has many factors and therefore, if all of them have to be become 0, that means all of them will become like this. So, this I would simply say check, convince yourself, check this. So, what is the ring therefore? Therefore, Z modulo this annihilator is 0. This annihilator is 0. So, this is the ring Z and the ring Z is not Artinian, because there is a descending chain of ideals which is not stationary. Alright. So, we have to correct the above theorem. So, I will just state it and leave the proof to you. The proof is very analogous. So, this is the theorem. A commutative, A ring, and V is an Artinian, V the finite A module. Now, I have added this finite here, then the following are equivalent. 1, V is an Artinian module, over A, and 2, the ring A modulo the annihilator of V is an Artinian ring. Proof similar to the above theorem. So, only one property of the Artinian ring which I will mention here now is, let me write it as a small lemma. This is very useful. If you have, let A be a ring, if A is Artinian, then every prime ideal in A is maximal. So, that is spec A equal to SPM A. Proof. Enough to prove that an Artinian integral domain is a field. Okay, so take any Artinian domain A, Artinian integral domain A, I want to prove it is a field. So, that means I have to check that every, if I take any element A here which is non-zero, then I want to prove that A is a unit. This is what I want to prove. So, what does that mean? That means I have to, let us look at lambda A map. Similar proof we have done in earlier in many times. So, this is the multiplication, left multiplication by A. So, this is any B going to AB. This is clearly a module homomorphism. This is an A module homomorphism, A module homomorphism. And because A is an non-zero element in an integral domain, this map is injective. So, that means it is an injective endomorphism of the Artinian module A, but then we have proved earlier injective implies bijective in case of Artinian. Therefore, it is bijective, lambda A is bijective. That means A is invertible, because then 1 is in the image, that means there exists a B such that AB equal to 1, and we are in a commutative case, therefore, A is a unit. So, this is very simple. Now, the next I will prove that Artinian ring has only finitely many maximal ideals, and therefore, that will be almost our relation between Artinian ring and Noetherian ring. So, I will prove that every Artinian ring is also Noetherian, and every non-zero prime ideal is maximal will mean that dimension of the ring is 0. Dimension means the crude dimension, which I will come eventually in this course later part, but all these things will be useful that time. That is why I noted them now, and the next time now I want to start with some properties of the Zariski topology back to geometry, and again we will come back to algebra and back to geometry. This is what we will keep doing in this course. So, thank you, and I will stop here and we will continue next time.